Good afternoon. Welcome to another exciting episode of Dave Does Math from Home. Today we're doing part 2 of our video on analytical limits, section 2.3. So we're going to be looking at functions described using equations, formulas, expressions, and we're going to be doing limits of those by manipulating the expression in the equation, mostly by plugging in numbers, a little bit. So in the first part of this video, we talked about the plans A, B, and C and how they applied to a rational function. We're going to look at a couple other kinds of functions here, see what those turn into. We'll start with polynomials. F of x equals, let's say, x cubed minus 3x plus 7. If I want the limit as x approaches 2 of f of x, I'm going to start with plan A. Plan A means I'm just going to plug in this number. 2 cubed will give me 8. 3x will give me minus 6. And plus 7 on the back end, this will give me 9. In yesterday's videos about chapter 1, I talked about polynomials as being no weird stuff. And I say that one of the best things about polynomials is that they're really well behaved. They're always continuous, they're always differentiable, they're always smooth. This is kind of what I mean by well behaved. If you take the limit of a polynomial, it will always be plan A. It's going to be plan A all the time, every time. There's nothing that could happen in this plan A polynomial land that would cause you to get something undefined or to cause this to fail. It's always just going to mean plug in the number, which is nice. I like it when things are easy. Let's look at another one. Let's do g of x equals e to the x minus 4. This is an exponential function that has been shifted 4 units to the right. If I want the limit as x approaches 7 of g of x, almost wrote f of x there. Once again, I'm always going to start with plan A. Plan A means I'm going to plug 7 right into this function, so it should give me e to the 7 minus 4, which is e cubed. And that's it, I'm done. Exponential functions are also always well behaved, always smooth, always continuous, always differentiable. So again, exponential functions will always give you a plan A sort of limit. Polynomials will always give you a plan A sort of limit, which is very, very nice. It also means that you're probably never going to see limits for polynomials and exponentials again. The tool of limits is useful for us because of what the information that it gives us when we end up in plan B or plan C. If we're doing things that are always going to end up in a plan A situation, we might as well just be evaluating the function. So talking about the limits of polynomials doesn't really make a lot of sense. It's just going to be, you might as well just evaluate the polynomial. You'll get the exact same thing, and you don't have to involve weird terms, weird vocabulary to get there. So let's do some other stuff. We'll talk about the limits of logarithms later. Let's do another rational function, because those are fun. Let's do f of x equals x squared minus 16 over x squared plus 5x plus 4. I want the limit of f of x as x approaches negative 4. We'll start with this one. Plan A means we're going to plug in negative 4, and we'll get 16 minus 16 over 16 minus 20 plus 4. This will give me a 0 over 0. That's not going to work. I'm going to need to simplify this as we scoot into plan B. Plan B means we're going to simplify this, see if we can get rid of whatever part of this is causing the problem, and then plug the number back in. Simplifying it usually means we're going to factor the top and the bottom, see if anything cancels. In this case, the top and bottom factors into x plus 4 and x minus 4. And the bottom factors into x plus 4 and x plus 1. So as long as x doesn't equal 4, negative 4, I can cancel these guys. Good news, x doesn't actually equal negative 4. It's going to get close, but it's never going to be equal, so we're safe. And this function is just going to be x minus 4 over x plus 1. So, we're going to go to plan B. Plan B is going to be plugging this x value into the simplified function, which will give us a negative 8 on top and a negative 3 on bottom, which simplifies into 8/3. And we're happy with that one. No problems with 8/3. Let's also talk about the limit of f of x as x approaches 10. This will give us 100 minus 16 from plan A. I'm just plugging this into the original. Give us 100 minus 16 divided by 100 plus 50 plus 4, which is 84 over 154, which simplifies into 42 over 77. It's a good number. I'll take that number. So in this case, plan A worked. It means that what the function looks like it's doing is what the function is actually doing, and we're all set. This is kind of why rational functions make such good limit problems. Sometimes plan A works, sometimes plan A doesn't work, and you have to go to plan B to get the y value of the little hole in the graph, the empty dot. And sometimes neither work, and we have to go to plan C and acknowledge that we have some sort of horizontal asymptote or vertical asymptote. I think we can probably all tell already that if we did the limit of x equals negative 1, that would put us in plan C situation, because that's the x value that will make even the simplified version of this not exist. So there's one more really important technique that I want to talk about in terms of simplifying these things. And for that, we're going to have to look at kind of a goofy looking function. Let's say f of x equals x, we'll do x minus 4 divided by the square root of x plus 5 minus 3. This is like a rational function, except there's a square root in the bottom. It's not a polynomial divided by a polynomial. I don't think there's any really easy, good way to classify this function. It's just a weird nonsense function. So let's find the limit of the weird nonsense function as x approaches 4. And as always, we start with plan A by plugging in x equals 4 and seeing what happens. When we plug in x equals 4, the top is going to give us 0. The bottom is going to give us root 9 minus 3. You're probably seeing the problem here. We're going to get 0 over 0, and that is a big frowny face. It's not going to work for us. So we need to go to plan B, Plan B is going to involve simplifying this. And in this case, simplifying this is not something that we've done before in pre-calculus. When we come to these problems and they involve simplifying the rational functions, we did that in pre-calculus all the time. We know how to factor the top, we can factor the bottom. That's old hat. We're great at that. We have not yet had to simplify something that looks like this. Unless you count some of the stuff we did with complex numbers. When we were dividing two complex numbers, the trick to dividing them was to multiply the top and bottom by the conjugate of the denominator. That's how we divided two complex numbers. We're going to try the same trick here. I think that this weird square root on the bottom nonsense might clean up really nicely if we could multiply by the conjugate. So I'm going to try that. We're going to multiply top and bottom by x plus 5 plus 3 and x plus 5 plus 3. This is the conjugate. The square root is the first term, the 3 is the second term. In the denominator they are subtracted, so the conjugate is going to have those same two terms with the opposite sign. Conjugate doesn't mean change all of the signs, so I'm not going to switch this out for an x minus 5. This is just one term and it stays x plus 5 in both. Conjugate just means that between these two pieces, the square root and the 3, we're going to change the operation that is between those two things. So now let's pause and see what happens here. I think I'm going to have to erase plan A to give us more room. We know that plan A is failed. We don't need that here anymore. On the top, I'm not going to try and simplify this at all yet. I'm just going to leave that alone. We'll call that an x minus 4 square root of x plus 5 plus 3. I could FOIL that out later if I really need to. For now, I'm just going to leave it like that. An x minus 4 and this conjugate thing. On the bottom, I have to FOIL this. This piece times this piece. We're going to multiply them together. So the first should give me an x plus 5. Square root times the square root. It's just the thing itself. So I have an x plus 5 here. I'm going to get minus 3 square roots of x plus 5. I'm going to get positive 3 square roots of x plus 5. And I'm going to get a minus 9 on the back end. If you remember from doing complex numbers, the really beautiful thing about multiplying by a conjugate is that these middle terms with their ugly square roots in them disappear. And so all I'm really left with is x minus 4 times x plus 5 plus 3. The x minus 4, the original numerator, times the conjugate. On top, x plus 5 minus 9 should give me an x minus 4 on the bottom here. Which works out really, really nicely for me, because as long as x is not equal to 4, we can cancel that. And this whole thing is really just root x plus 5 plus 3. This is how you simplify weird nonsense functions with square roots in denominators. So you multiply the top and the bottom by the conjugate. So that's the simplification done. Now we get to the easy part. We take the limit as x approaches 4 of f of x using plan B. And that just means we're going to plug this in here. I know that x can't equal 4, which is why I'm taking a limit and not doing a function evaluation, because the limits are safe. So I'll get the square root of 9 plus 3. The limit is 6. So that's weird and nonsensical, but it works. And that's what's important. There's going to be, I think, at least one homework problem that looks like this, and it'll come back later in Chapter 3, which is why we're doing it right now. Most of the problems you're going to get are just going to be rational functions. They're pretty straightforward. If you end up in Plan B, you just factor, cancel something. If that still doesn't work, you end up in Plan C, you give up, the limit does not exist. Throwing all this weird limit notation at you and this whole new idea of a limit with 3 different plans feels like a lot. It's not actually as bad as it seems. Do the homework, maybe do the homework twice. If you get enough practice and experience, this will all come very easily. It will be second nature, and then you'll do really, really well on our first test. That's the goal.